Okay, thank you very much. I first of all want to thank the organizers for their kind invitation. And the title of my talk is First and Second Sound in Two-Dimensional Bosonic and Fermionic Systems. And this research activity has been done in collaboration with Alberto Noni, Koichiro Furutani, Giacomo Beghin, and Alberto Capellaro. Here there is the summary. First, I will briefly review the Landau theory of superfluids and in particular the equation for deriving the first and second sound. Then I will apply this theory to two different cases, namely weakly interacting two-dimensional Bose gases and two-dimensional Fermi gases in the BCS-BC crossover. And finally, some conclusions. According to the Landau's two-fluid theory of superfluids, the total number density of a system in the superfluid phase can be written as the sum of the superfluid density and a normal density. In the equation 1, n is the total density, n sub index s is the superfluid density, and n sub index n is the normal density. Obviously, at the critical temperature, Tc, one has that the normal density is equal to the total density, and correspondingly, the superfluid density is 0. Following Landau, in a superfluid, a local perturbation excites two wave-like modes, first and second sound, which propagate with velocities that are here I denote as u1 and u2. These velocities are determined by the positive solution of the algebraic b-quadratic equation 2. You see, this is a b-quadratic equation. The unknown quantity is u. The two solutions, u1 and u2, are the first and second sound. And in the equation, you see appear other quantities, C10, C20, and Ct, that now I will describe. So you need for sure these quantities to get the solution of the equation 2. In particular, C1, that is sometimes is also denoted VA, is nothing else than the adiabatic sound velocity, which is obtained doing the partial derivative of the pressure with respect to the density at fixed entropy and volume. Instead, C20, that is sometimes also denoted as VL, is the so-called entropic or Landau sound, and it is obtained by equation 4. And you see in the equation that you need the entropy of the system, and you have to also to do the partial derivative of the entropy with respect to the temperature at fixed number and volume. But you also need the ratio between the superfluid density and the normal density. And finally, Ct, that sometimes is also denoted as Vt, is the familiar isothermal sound velocity, namely related to the partial derivative of the pressure with respect to the density at fixed temperature and volume. And so, clearly, if you want to determine these three velocities, you need the pressure, the equation of state, and also you need the superfluid, the ratio between the superfluid density and the normal density. Let us now apply the problem to the two-dimensional weakly interacting Bose gas. The Helmholtz free energy of a weakly interacting two-dimensional gas of identical bosons of mass m can be written. Here I use h bar equal to kb with Planck constant, the Boltzmann constant equal to 1, as in equation 6, namely the sum of the contribution, where capital F sub n 0 is the mean field 0 temperature free energy, F sub index Q is the quantum contribution at zero temperature, and Ft is instead the thermal contribution. Now, the idea here is that everything can be derived from the elementary excitations of the system, and the elementary excitation in this case of a weakly interacting Bose gas with constant interaction strength G are given by equation 7, that is the typical Bogoliubov spectrum of the elementary excitation. Knowing the elementary excitation, you can determine the three objects in equation 6. Actually, the first object can be also determined without the elementary excitation, that is the mean field contribution to the Helmholtz free energy, but the quantum fluctuation depends on the excitation spectrum, the second term, and clearly also the third term, the one that depends on the temperature, is strictly dependent on the elementary excitations. The quantum correction, FQ, in the free energy, as written, is ultraviolet divergent and requires a regularization procedure. Dimensional regularization leads to equation 8, where you see it appears this logarithm, and in the logarithm you have inside the logarithm numerator a cutoff energy, this epsilon lambda, which is however related to the physical scattering length, two-dimensional scattering length A to D of the system, and at the denominator inside as an argument there is the strength G and the number density. And obviously there are other terms, and everything scales as the G times n to power 2. Here there appears also gamma in the definition of the cutoff energy, and this gamma is the, let's say, familiar Euler-Mascheroni constant. Moreover, eta that appears in equation 8 is a dimensional gas parameter as defined in equation 9. Moreover, one finds a relationship between the cutoff energy and let's say, interaction strength G times n that is given by equation 10, related to the number of particles, total number of particles, and to the gas parameter. All the thermodynamic quantities, as I said, can be obtained from the Helmholtz free energy. For instance, the pressure P can be obtained as the partial derivative of the Helmholtz free energy with respect to the area at fixed number of particles and temperature. The entropy is instead the derivative, the partial derivative with respect to the temperature of the free energy divided by the total number of particles, calculated at fixed number of particles and area. Instead, the normal density, and obviously consequently also the superfluid density, can be extracted from the familiar Landau formula, which again relates the normal density to the elementary excitation of the system according to equation 13. So by solving equation 13, which contains the Bose-Einstein distribution, actually the derivative of the Bose-Einstein distribution with respect to the energy, calculated at the energy given by the elementary Bogoliubov-like elementary excitations, and doing the integral, you get the normal density. And so you have, at least numerically, you can calculate everything, and you can compare with the experiment. However, the Landau formula for the normal density does not take into account the formation, the possible formation of quantized vortices and anti-vortices by increasing the temperature. These quantized vortices are indeed crucial for the two-dimensional Bose gas to obtain the phenomenology predicted by Berezinski, Kostels, and Towles. In general, the presence of quantized vortices renormalize the superfluid density and we can get this renormalized superfluid density by solving the Nelson-Kosterlitz renormalization group. Maybe Nelson-Kosterlitz-Thouless, here there should be written Thouless, the renormalization group equation, given by equation 14. You see, in equation 14, there are two variables that depend on a fictitious time t, and these variables are this capital K, that is nothing else than the superfluid density divided by the temperature, and at fictitious time 0, you insert the bare superfluid density, and at time that goes to plus infinity, you get the renormalized superfluid density, obviously calculating this capital K at fictitious time that goes to plus infinity. In the equations appears also this y, and this y is related to this mu c, and this mu c is the vortex chemical potential. And again, you have to fix this vortex chemical potential at the fictitious time 0, so the bare vortex chemical potential, and solving the equation for a long time, eventually you get the renormalized chemical potential. Within this procedure, yes, in general, for 3D superfluids, the transition to the normal state is a BCE phase transition, while in 2D superfluid, the transition to the normal state is something different, is a topological phase transition. And what is truly relevant is this plot where you see a comparison of the superfluid fraction as a function of the temperature in a three-dimensional case and the two-dimensional case. You see that in three-dimensional case, in general, the superfluid fraction goes to 0 smoothly, while in the two-dimensional case, the superfluid fraction has a jump to 0 at the critical temperature that obviously is the Berezinski-Kosterlitz-Thouless critical temperature. So this is the main difference between the three-dimensional and two-dimensional case. Now, within this machinery, we were able to compare our theoretical result with recent experimental data of a paper published in Nature last year. And you see, our results are the solid lines. The blue solid line is the first sound. The green solid line is the second sound that obviously goes to 0 at the Berezinski-Kosterlitz critical temperature. Notice that in the horizontal axis we have the scale temperature, so the temperature in units of the critical temperature. And also in the vertical line, we have a scale velocity, and it's the velocity in units of the Bogoliubov velocity that is given here simply by the strength G times the density. And you see the comparison between the theory and the experimental data is quite good, I would say. And our results are published in New Journal of Physics. Now, I changed the topic, but the system under investigation. The topic is the same, but the system under investigation is different. And I consider a two-dimensional Fermi gas in the BCS-BC crossover. As you know, in 2004, the three-dimensional BCS-BC crossover has been observed with ultracold gases made of two-component fermionic atoms. This crossover is obtained using a Fano-Feshbach resonance to change the three-dimensional scattering length AF of the interatomic potential. More recently, also the two-dimensional BCS-BC crossover has been achieved experimentally with lithium-6 atoms. with two components lithium 6 atoms. Contrary to the three-dimensional case, two-dimensional realistic interatomic attractive potential